Greetings, physics enthusiasts. Welcome to AP Physics 2, Unit 6, Lesson 10. This is our final video in Unit 6 on optics. So let me remind you that last time, for the previous video, we talked about Young's double slit experiment, where light is going to travel and it's going to encounter two slits and then hit a screen. And one way of thinking about this is that either light goes through here and makes a dot here, or light goes through this slit and makes a dot here. So we might expect two little dots. But because light is a wave, it turns out that all of the light goes through both slits and can travel, to this point. It could travel here and here. And you see those two distances are different. And it can go to this point, and it can travel this way and this way. And those two distances are different. But the amount of difference, or the path difference, is different for the upper dot as for the lower dot. Anyway, so we talked about the math, and we said that when the path difference is an integer number of wavelengths, we get constructive interference and a bright spot. And when the path difference is an integer plus 1/2 number of wavelengths, then we get a dark spot, or a minimum. And so, again, this is review from the previous video, 269. Feel free to review it if you want. But we came up with this equation, d sine theta, and this is for bright, B-I-R, B-R-I-G-H-T, bright, d sine theta bright equals m lambda. So d was this distance here, which is called the slit separation. And then the angle is the angle from straight across to the point we're talking about. That would be theta, right there. If I wanted the angle to give me not brightness, but darkness, I would replace m with m plus 1/2. All right, so that was the equation for Young's double slit experiment, 1-2 slits, or a double slit. And that is that is the primary way that we prove that light is a wave. I mentioned in a previous video that we'd already talked about light being a particle. Shh, actually, that's an upcoming video. It'll be very exciting. So fret not. Now, sometimes I'm going to change colors here and draw a different experiment. Sometimes instead of having two slits, we just have one slit and then a screen. And so the light comes through this one slit, and you're thinking, well, there's just one slit. Of course, the light's just going to go across and give me a little illumination right here. But actually, when the light goes through a slit, it spreads out and gives us a pattern, again, of bright, dark, bright, dark, bright, dark, bright, dark, bright, dark. And the bright is in the center. And so that, again, is called an interference pattern. Interference is when crests give constructive interference when they're together, and troughs give constructive interference when they're together, and crests and troughs, when together, give destructive interference. Remember, constructive interference gives us what we call a maximum, or brightness. Destructive interference gives us a minimum, or darkness, bright, dark, bright, dark. And we could have the same idea of going straight across being an angle of 0, and not going straight across gives us a different angle. Now, I'm not going to derive it for you. It's in your book, so feel free to peek at it if you want, but I'm going to show you the equation. Now, here's the equation in the book. Sine theta equals m lambda over a, where a is not the distance between the slits, because there aren't two slits. There's just one slit. So a is the width of the slit. How wide is the slit itself? So it's this distance. But look at these two equations. Look how similar they are. Sine theta, m lambda, And there's a distance here on the left, and there's a distance here on the right, but oh, it's in the denominator. So could I move this A over here? Yeah, I could. So I don't like that equation. And instead of calling this slit width A, I would rather call this slit width D. And then look at this, D sine theta equals M lambda. Oh my goodness gracious, it's the same equation. So why make the equations look different when you can make the equations look the same? Same equation. The only difference is that this, for the single slit, gives you not the location of the first bright fringe or stripe, but it's the first dark one. That is the one difference you have to remember about this equation, is that for single slit, it gives you where darkness happens. For double slit, it gives you where brightness happens. And you might be saying, oh, gee, if you'd drawn that bigger, it'd be easier to see. But you're also thinking, he's kind of dividing his paper into thirds. You are right. So let's see, we've got purple, we've got green. Let's go for another of my favorite colors, my third favorite color, black, purple, green, and black. Green's my real favorite, but I also like purple and black a lot. So there's one more kind of situation that we could have, and that is where we don't have one slit, we don't have two slits, we have lots of little slits. Lots of slits, and then a screen. And so the light comes through, and as you can guess, we're going to get what's called a interference pattern, an interference pattern. In the center, we have something bright, dark, bright, dark, bright, dark, bright, dark, bright, dark. So going across, there is our brightness right across from the center. This angle would be 0, and then this other angle here would give us brightness or darkness according to, can you guess what the equation is going to look like? Can you guess? It's the same equation. D sine theta equals M lambda. Pardon me. D here was the slit separation. D here was the slit width. D here again becomes the slit separation. So D for each pair of adjacent slits is the same. And again, just like the first one, it's for, this gives us bright stuff. Okie dokie. So we have the same equation. When there are multiple slits, more than one, this angle gives us where we find bright stuff. When there's only one slit, the angle gives us where we find dark stuff. Let's look at some of the finer points here. This is double slit interference, Young's double slit. This is single slit. This is called diffraction. Single slit diffraction. The phenomenon when light is traveling as a beam and it goes through a thin opening and then it spreads out. That spreading out is called diffraction. So we call it single slit diffraction. This, where there's a bunch of these, is called a diffraction grating. A diffraction grating. G-R-A-T-I-N-G. When you're grating cheese on a cheese grater, that's the same word, grating. That pattern of little sharp things that cut off pieces of cheese is like this pattern of slits. When there is water running down the gutter in the rain, the water runs down the gutter for a while until there's this big hole and the water goes down underground to the sewer or whatever. But it's a big hole and we don't want, a bicycle or a pet or a person to fall down in that hole. So there is this grate, metal grate, that lets the water through, but not bigger, important things through, like people and pets. And so that grate is the same word as this grating, a regular repeated pattern or interval of space. All right. And then I think the final thing I had to say here is there have been some questions about this letter M, and it's just going to be an integer, 0 or 1 or 2 or 3 for bright here and dark here. And then if I wanted dark here or bright here, I would replace M with M plus 1/2. Now, the first number I'm going to plug in for M is 0, which would give me what's going on straight across. For these guys, we've got bright straight across. The first number I would plug in here for M would be 1. I know I've got bright straight across. So I wouldn't plug in, just a second. If I plug in 0, that would give me an angle of 0, and that doesn't give me darkness. So I would plug in, the first number I would plug in for M for this one would be 1. But if I were to replace this, for d sine theta dark equals M plus 1/2, be sure to put parentheses, times lambda. So the first number I'm going to plug in for M to get darkness is going to be 0. I'm going to want a path difference of a half wavelength. Whereas the first, I could plug in 0, but that would be boring. It would just give me straight across. So for the first place up here, I would plug in M equals 1. Just some people were wondering about, would I plug in for the first darkness, would I plug in 0 or 1? 0. All right. So anyway, these 3 equations are all one equation. This might be a great time to begin preparing for the AP Physics exam. Look online at the equation sheet for the AP Physics 2 exam and see if you can find this equation. Notice that I'm pointing at 3 things and calling it this. There aren't 3 different equations on the equation sheet. There's just one. Check it out. See how it looks like this. Did they use D or A? Did they put the distance on the left in the numerator, or did they put it on the right in the denominator? Regardless, it's the same equation, but you should know where that equation is on the equation sheet. That's they're telling you 2 things when they put the equation on the equation sheet. 1, don't bother memorizing it because here it is. And they're saying 2, but it's important. So even though you're not memorizing it, you should understand what it means and how to use it. All right. That's all I have for this final optics video. I hope you have enjoyed optics, and I hope to see you again soon when we study a new topic. Until then, don't break any of the laws of physics.